This is section 7.5, day 2. In letter A, we have use the parameter t equals x minus 1 to write the parametric equations that can represent y equals x squared plus 2. Then graph the equation indicating the speed and orientation. Let's solve for x in this equation right here. We have x equals t plus 1. And then we can replace x in this equation with t plus 1. We have y equals t plus 1 squared, then plus 2. That's equal to t squared plus 2t plus 1 plus 2. And then finally t squared plus 2t plus 3. Now let's make a chart. We have the t's, the x's, and the y's. And let's have t go from negative 3 to 3. 0, 1, 2, and 3. That way I can keep it on the screen. Then x is going to go, if negative 3 plus 1, that's negative 2, negative 1, 0, 1, 2, 3, and then 4. And let's find out what y is. If I plug negative 3 in for the t's here, we get 9 plus 6 is 15. We get 9 minus 6 is 3. 3 plus 3 is 6. Plug negative 2 in, we get 4 minus 4 is 0, and we get 3. Plug negative 1 in, we get 1 minus 2, that's negative 1 plus 3, that is 2. We plug in 0, we get 3. We plug in 1, we get 6. 2, we get 4 plus 4 is 8, plus 3 is 11. And then when we plug in 3, we get 9 plus 6 is 15. We get 18, and we're a little bit off the chart here. Let's plot those points. We have negative 2, 6, negative 1, 3, 0, 2. Then we have 1, 3, 2, 6, and then 3 is a little bit off the chart. That's up there 11, and then 4 is way up at 18. So we started at this point, and we worked our way left to right. So we'll indicate that with little arrows as we go along here. Use the parameter t equals 2x to write the parametric equations that can represent y equals x squared plus 2. Then graph the equation indicating the speed and orientation. We have x is equal to t divided by 2 when we solve for x here. And then y is going to be equal to t squared over 4 plus 2. Let's again go from negative 3 to 3. We have t, x, and y. Negative 3, negative 2, negative 1, 0, 1, 2, and 3. When we plug negative 3 in, for x we get negative 1.5. Negative 2 is negative 1. Negative 1 is negative 1/2. 0 gives us 0. Then we have 1/2, 1, and 1.5. Let's plug the t's in for y. We get 9/4, and then plus 8/4. That's 17/4. That is 4.25. 4.25. When we plug negative 2 in, we get 4 over 4. That's 1. 1 plus 2 is 3. When we plug negative 1 in, we get 1/4 plus 2. That's 2.25. 0 gives us 2. When we plug 1 in, we get 2.25. When we plug 2 in, we get 4 over 4. That's 1. We get 3. And then when we plug 9 in, we get 9/4 plus the 8/4. That's going to be 4.25. Let's plot those points. We have negative 1.5 and 4.25. That's about right there. Negative 1 gives us 3. Negative 0.5 gives us 2.25. 0 gives us 2. And then we go back up the same exact way. So there is again a parabola. And the direction is left to right. Projectile motion. For an object launched at an angle theta with the horizontal at an initial velocity v naught, where g is the gravitational constant, t is time, and h naught is the initial height. The horizontal distance given all these values is x equals t times v naught cosine of theta, and the vertical position is y equals t v naught sine of theta minus 1/2 g t squared plus h naught, where g is equal to 32 feet per second squared, or 9.8 meters per second squared. Shane Lechler of the Oakland Raiders has the record career punting average with an average of 46.47 yards. Suppose that he kicked the ball with an initial velocity of 26 yards per second. So initial velocity is 26 times 3, which is 78 feet per second. And we need to use feet per second for gravity, so we'll convert the yards per second into feet per second. At an angle of 72 degrees, theta is equal to 72 degrees. How far will the ball travel horizontally if he punts it with an initial height of 1 yard? H naught is equal to 3 feet in this case. We need the horizontal distance, which is x. X runs horizontally. We have x equals time times v naught, which is 78, and then times cosine of 72 degrees. We don't know what the time is, but we know that time is up when the ball hits the ground, and that's the vertical distance. So let's look at vertical distance. We have y equals t times v naught, which is 78, times the sine of 72 degrees, minus 1/2 times g. G's right there. G in this case is 32 feet per second squared, times t squared, and then plus 3 feet for the initial height. Let's plug this into the calculator, and we're going to find out when the ball hits the ground. We're going to find out how long that took. So we're going to grab our calculator. In y equals, we're going to put x times 78 times the sine of 72. Since we're using degrees in the mode, you want to make sure that you have degrees selected instead of radians. Let me get to the end here. And then minus 1/2, or 0.5, times 32 t squared, or x squared in this case, and then plus 3. What we're interested in is seeing when the ball hits the ground. In other words, when is the height 0 again? So we can graph this. This curve represents the height of the ball at any given time. Let's have a better window here. We can go from 0 to, I don't know, looks like it didn't go past 7. And then the height is a little higher than 10. How about, I don't know, let's go to 50, and maybe we go by 5s. Let's graph that and see how close we were. Not quite high enough. What if we go to the window and we go y max is, I don't know, let's try 80. Let's graph that. Not quite high enough, but close enough to kind of tell what's going on here. Now the height will be 0 right here, which is 1, 2, 3, 4 point something. Now we can find out what that number is by going to calculate. We want a 0, so we have number 2. And we can come over here and go to the left. It says left bound, left side, right side, and we'll back up a little bit for the guess. Turns out to be 4.676 seconds it takes for the entire flight. So now we're going to plug that in for x, 4.676 approximately. If you go to the home screen, quit, and you type in x, press enter, it has that value in there. Now to find the horizontal distance, we can just do x times 78 times the cosine of 72. The horizontal distance is 112 feet. This problem seems to be in yards, so we'll divide by 3. And it turns out that it was a 37.57 yards. Kenzie hits a softball with an initial velocity of 83 feet per second. So 83 is an initial velocity. At an angle of 34 degrees, theta is equal to 34. How far will the ball travel horizontally if Kenzie's bat was 3.5 feet from the ground at the time of the impact? So the initial height is 3.5. The horizontal distance is x, and that's equal to the time times the initial velocity, which is 83, and then cosine of 34. The problem is we don't know the time, and we're going to find that by plugging the y into the y equals and then graph and see when the ball hits the ground. We have t v naught is 83 times the sine of 34 degrees minus 1/2 times 32 feet per second, that's the g, t squared, and then plus 3.5. Let's enter this into the calculator. We have y equals x times 83, and we have sine of 34 degrees minus 0.5 times 32 x squared, and then plus 3.5. Let's graph this. And in the standard window, we're very close to a value of 3, so we can go second, calculate. Number 2 is a 0. I'm guessing to the left is 2, to the right would be 4, and we're somewhere around 3. The x value is 2.974. We can plug that in for x, and then go to the home screen, and we have x times 83 times, we have cosine of 34. And the answer is 204 approximately, which on this one the answer is letter B, 205.